which would be third session series in our digitalized surface manufacturing EPSRC Network Plus event of what we call it as monthly featured webinar. So I would like to now invite the speaker for today. As such, he needs no introduction. He's coming from a small enterprise called Polytech. The name of the speaker for today is Mr. Joe Armstrong. He educated himself in Bedfordshire, England, and was qualified in computer electrical engineering. And he has been leading many surface metrology events across different industries, and now works at Polytech after gaining experience from all the industries. He has more than 25 years of experience, and much of his work has been about laser technology, optics, and metrological applications, both in dynamic and static surface topography modes. And I have seen him personally being, very much involved in wide range of instruments, tackling their installations and commissioning. So by now, I would say he's an international expert, and he receives formidable support from Polytech Germany, which is directly establishing many active partnerships throughout the UK and beyond. So without further ado, let me invite Joe and share with us all as to what he would like to show us today from the metrology perspective. Joe, over to you.
Hello, Sarav. I hope everyone can hear me nice, loud and clear. Is my sound okay, Sarav?
Yes, you're okay. Audible, Joe.
Okay, brilliant. Thank you for the very kind introduction. I will just turn my video off to help my internet, because I have to share my screen, so it'll help with the, and I'll turn my video on again towards the end for any questions that we have, okay?
Sure.
Okay, so firstly, thank you for everyone who's joined today and is taking the time out of your lunch break to take a look at Polytech. So this is a presentation which should take between 30 to 40 minutes. So I hope I do not interrupt your lunch too much. So if I get straight into the presentation, Polytech as a company was founded in 1967, and we've been associated with optical instrumentation for many years now. Our first introduction of our main product line, the laser vibrometer, was introduced to the market in 1987. Our breakthrough in surface metrology, my area of expertise, came in 2004. And in 2017, we celebrated 50 years of being in business. Polytech as a company is a medium-sized company, and we have over 200 employees in our headquarters in Waldbronn in Germany. So today's webinar goals is just to answer a few simple questions. Why optical metrology? To talk about our technology, coherent scanning interferometry. A quick overview of products and applications. I have 2 case studies which specifically relate back to additive manufacturing and, in addition, digital data processing. Then we finish with conclusions, and I hope we have some questions towards the end of the webinar. So TMS, Topmap, surface metrology from Polytech. So at the beginning, why surface metrology? Well, different surfaces have different functions and they have different performance. Surface topography has an effect on a wide range of application properties, such as formability, friction, wear, visual appearance, bonding behavior of paints, coatings, corrosion resistance, fatigue behavior, sealing capacity, electrical and thermal contact resistance. So surface metrology proves to be an important feedback mechanism for any manufacturing process. And here I give an image of an additive manufactured 3D printed surface. So typically in the market, you'll see the most accepted method of surface measurement is the starless method. So many manufacturers have to start by asking themselves, why change to optical from a stylus method? The first answer is some materials require non-contact measurements. They could be soft materials, for example, rubber. And of course, you do not want to cause damage to either the surface or the stylus. The second answer is aerial measurements are becoming faster and easier. And it should be noted that aerial measurements now lead the way in research. Your third answer is you get simply more information. You do not miss features. If you consider the human eye and how we look at the surface, the human eye brain has a very good pattern recognition capability. So when we visually inspect a surface, we can do things that a machine will have challenges in doing, such as identifying the lay of a surface, scratches, defects, and the visual overall appearance of a surface. So for our Topmap product family, we have a range of products. We have the very successful ProSurf products. These are a macro lens system. Then we have our newly introduced this summer microscope type products in the Microview and the Microview Plus. Then we have some inline products, and we have our entry level MetroLab product. So we have, very interestingly, the complete solution from micro to macro measurements. Because we're using coherent scanning interferometry, all our Z resolutions are to the nanometer or sub-nanometer. And we refer to our measurement capability as deterministic because it's not focus driven. So we get the high Z resolution irrespective of whether we're using a macro lens system or a microscope lens system. So how do we do this? Well, we're doing coherent scanning. So with coherent scanning, we're taking effectively what is a white light interferometer, and we are scanning a white light interferometric signal through a surface. So we do this for each single pixel that's on the camera detector. And by scanning through the surface, just set off a small graphic, what we do is we capture the intensity signal coming back, and we collect that information, and then we look at the phase information contained within the coherent scanning, and we signal process this correlogram information. And by signal processing this correlogram information, we can process the data in such a way that we can go beyond the diffraction barrier of light, and we can get sub-nanometer Z signal processing in Z. So effectively, we are identifying the best focus of a surface. So why coherent scanning interferometry? Well, first of all, you see your surface. So as you can see, if you have a surface with scratches on it, it's very easy to see and identify these scratches. These particular scratches are in the order of 15 nanometers. Our measurement is non-destructive. The technology has proved very stable and reliable and robust. You can analyze over an area, not just a line. And our technology is proving well accepted in both R&D and especially the manufacturing settings, where most of our sales to date do go. We can measure a variety of materials, so whether it's black, smooth, shiny, bright, dark, even combination surfaces. With our smart scanning, we can take care of all different surface types and varieties. And of course, our data is deterministic in Z. So I always like to talk about how big and how small. For how small, you start with the microscopic type system, and for how big, you can start with the macroscopic type system. So a microscope will make small things look big, and you can see the optical performance starts from 0.46 microns, and the point-to-point spacing, because the digital sampling rates are much higher, start from 0.06 microns. Whereas a macroscopic system is making larger things look big. You'll notice we have a very interesting vertical measurement range. So it's actually possible to measure a 70mm step without crashing into the artifact that you're measuring. The working distance of a macroscope system has a standoff distance of 83mm, and within a single measurement you can get up to 45mm. With stitching, you can go far beyond that. So what is the basic difference between large area and microscopic system? Well, first of all, with a microscopic system, you tend to be working much closer to the surface. You're then turning the light faster. By turning the light faster, you get the benefits of higher XY sampling rates. But of course, you reduce your field of view. And if you look at the telecentric lens, you can see you have a much larger standoff distance. You have a much improved field of view. But equally, you get very good penetration into deeply recessed surfaces. And this is a function of the low numerical aperture. Naturally, the microscope systems will handle higher sloping surfaces much better. On smooth surfaces, you could typically get maybe up to 40 degrees. On surfaces that have micro-texturing or surface roughness, these values can even jump up to 85 degrees. With the macro lens system, you can equally get some very impressive slope measuring capability. Typically, if you're measuring a mirror, you might be restricted to 2 or 3 degrees on a super finished surface. But if you start to measure cones and they have some micro nano texturing, you can easily achieve 60 to 70 degrees of slope. So the microscope system, if you want to measure larger areas, you have to do image stitching. Whereas a macroscope gives you access to a different range of spatial frequencies. You simply see more of the surface. So to further explain that, here on the left, we have a microscope image. And you can see the very fine texture, you can see the fine step height details, and you can really see all the details of the surface. The red arrow points to an image as taken of the same structure from a macroscopic system on the ProSurf. And you can see here, we get a very good overview of the surface. We can now see, instead of the grass and the leaves on the tree, we're seeing the lines of a football pitch. So we can see where the goalposts are, we can see where the goal lines are, and we can see the lay of the land. So the macroscopic system gives you like a global view of the texture, the form, and the steps, whereas the microscopic gives you a higher spatial frequency information. So what do we want to measure with Polytech equipment? Well, we certainly like to measure form parameters. For our ProSurf, measuring the flatness of large areas such as a wafer for wafer bow is a very popular application. Sealing surfaces is a very popular application. Of course, we can measure parallelism. So if you want to measure the intersurface relationship, the macroscopic system is particularly good at those types of applications. And we can get many other dimensional informations for you. We can naturally measure step heights. So here you got a stepped feature, and you can see a machine feed error. So you can measure step height information. Of course, we can measure roughness, and that will present you with surface texture information. And of course, tribology, so looking at scratches and defects of a surface. And finally, we're particularly interested in automated measurements. So if you have multiple samples and they all fit within a single field of view, we can do multiple processing for our pattern matching, and you can have fully automated measurements. So a quick introduction to the Topmap microview. We name the product TMS 1400. So we've got the measurement head. This has a 100mm Z range and uses our continuous scanning technology. So position equals measurement. So if you want to measure sub nanometer, 100 microns, that's possible. If you want to measure sub micron, a millimeter, that's also equally possible. Of course, it's mounted on a stand. We have a selection of objective lenses going from 2.5 to 100 times. These are all turret mountable. As a product function, we have focus tracker and focus finder. The focus finder is additional hardware, so it goes above and beyond the traditional pre-scan that people can have with these instrument types. And of course, you've got motorized stages. We've got both manual and motorized options, and all our specifications relate back to the FAIR data sheet, so you have comparable parameters. For our more advanced TMS 2400 product, which we call the Microview Plus product, this has a more open architecture, so you can have more flexibility in the instrument's setup, configuration, and size of components you may wish to measure. The measurement head has the 100mm Z range with the continuous scanning technology, but now we have two additional interesting possibilities. The first is this measurement head is closed loop, so you have a feedback mechanism, so you reduce your measurement uncertainties in Z. Plus, you can have a color information option available for this product. The turret now is both motorized or manual, and you have both available focus finder and focus tracker available. The stages now increase with a standard 200mm option, and you can have on top of this both manual and motorized tip tilt options available, and you could even have larger stages on request if desired. And again, specifications compare to the FAIR data sheet protocols. So for microscope type applications, we're popular throughout various industries, including medical, automotive, aerospace, optics, scientific and electronic industries. So applications that interest us are surface coatings, textured materials, microparts and optics, precision machining, material science, surface defects, tribology, and of course micro devices. Our Z resolution is exemplary. We have Z resolution down to the sub-nanometer. Here I have an example of a scratched surface, and you can see the SA, which is the aerial equivalent of RA, and the surface texture is 0.224 nanometers. Within the profile, you can see a 500 picometer scratch, and the sensitivity in the order of 35 picometers. People always ask, is this real? The nice thing with the human eye interaction, you can measure an area, you can then view the scratches and the features within the surface. You can then physically shift a surface in an X or a Y direction, and you can see whether all these features contained within the surface move in translation to your XY movement. And with this particular case, is exactly what we did, and all these features moved. So the Z performance is amazingly excellent. So we're ideal for measuring small step heights. Here we have a small step height in the order of 10 nanometers. We can measure tribology. Here I have an example of measuring corrosion. The image on the left is how a typical pseudo color image would be viewed. But of course, this is a corrosion measurement. The image on the right is a vivid graphic representation in colour of how this surface appears on the Microview Plus. And here you can see much more clearly how the surface texture is changing in the corroded areas to the non-corroded areas. And of course, just to further demonstrate how colour views, here I have some polymer sitting on glass, and you can see I have red polymer, green polymer, and blue polymer. And of course, you can measure surface textures, steps, volumes, widths, distances, thicknesses, surface defects can all be seen and viewed. So a quick introduction for our ProSurf, which we consider our premium product. It has many uniqueness in terms of features on the market, such as the long standoff distance, the high scan ranges, the large field of view. But one of the most interesting features about this product is contained within its structure. The Z translation isn't done by a piezo device, it's not done by a stepper device, and it's not done by a servo type device. It's actually being translated in Z through a floating magnetic drive. So it's a low friction force surface. Sort of imagine it like one of these high-tech Japanese trains. So by taking this approach and by using coherent scanning interferometry, we get the nanometer sensitivity, but then we get the low friction force surface. And we have this incredible capability where we can easily measure to 1 or 2 microns step height, reproducibility, and measurement uncertainty over 40, 50, 60 millimeters. So for the large area type applications, we like measuring flatness. Of course, we're measuring wide areas very quickly. We can measure hard to reach areas. So the telecentric optics has very good penetration into a surface. And we can measure multiple objects at the same time. We have a long working distances, long scan ranges, and of course, we have a multi-sensor version of this instrument where we can put a confocal optical probe, so this can increase your spatial frequency bandwidth. So although the large field of view has the disadvantage of a larger high frequency spatial sampling, so the spatial sampling starts from 8.4 optically and 14 microns digitally, with the addition of the roughness gauge, you can get down to the micron. So applications that suit the macro type system are sealing surfaces. You can get some representation of roughness or waviness. Fuel injectors, so multiple measurements quickly. Tribology, here we have the cartridge of a gun from a bullet. Industrial components which are complex, and of course macro shapes such as watch components. So now moving on to some case studies. I'm starting with a case study for additive manufacturing, and people are always very interested in trying to understand the surface roughness of AM printed surfaces. And this is because you can print complex shapes. The shapes are at different angles, and you're always trying to understand the relationship between the angle, the shape, and the texture. And here I have a variety of surfaces that have all been measured. And for this specific image, you can see that these are all measured and imaged with the ProSurf product. If you think about AM surfaces, you're normally taking something like a 20 micron ball, sticking it on a surface, melting it. So the digital sampling of a ProSurf starts from 14 microns. So you can see it's quite well matched to the smallest types of features you may want to see in terms of texture representation. So for all our instruments, we measure textures, and these results can relate back to ISO guidelines. So 25178-2, ISO 4287 and ISO 4288. It's worth mentioning at this point that my colleague Wilfred Bauer is the lead in writing up the aerial 2578-2 parameters for the ISO committee at the moment. So Polytech as a company is intrinsically involved and active with ISO and its committees. So surface topography, in nature, surfaces are 3D. For many surfaces, a single line cannot easily help you identify pits, valleys, peaks, and ridges. If you consider the function of a surface, if you want to fully understand the functionality of a surface, aerial measurements will be much more descriptive. But of course, you have to appreciate profile measurements are much more well established and more fully understood. Here I have two examples. One on the left is a surface. You can see the texture in the X direction is different to the texture in the Y direction. And I have a wear scar up on the top right, and you can see that the peaks and valleys are non-symmetrical. So to have an aerial measurement is certainly an advantage when you come on to trying to understand the complex interactive behaviors of surfaces. So for any measurement or analysis of a profile section, even if properly controlled, will only ever give you an incomplete description of a real surface topography. For a fuller description, aerial measurements are always far more comprehensive to the function of a surface. Here I have a comparison of small area to large area. These are additive manufactured printed surfaces. And the image on the left is a close-up view taken with a single measurement from a microscope type system. It's always interesting to ask the question, when does shape become texture? Clearly, the single image must be shape. If we step back, now we can start to see some reproducibility of the surface. But is this stable enough to call texture? Is the parameters that we achieve from this size object going to give us a stability in terms of surface texture so we can predict and relate that to the manufacturing processes? If you think about the image on the left, it's like looking at the leaves on the tree, whereas the image on the right is looking at the tree. But maybe what we need to do for the surface texture is look at the woods of the tree to really understand the lie of the land. So microscopic images are great for getting fine, close-up representations of how a surface texture. I would argue that for something like an additive manufactured surface, where you're measuring a surface that has inconsistencies within its surface texture, it's lumpy, bumpy, it's not very even, the macroscopic system will interestingly give you a much greater appreciation to the overall stability of the surface. So if you really want to understand the variation of a surface, the macroscope complements very well the microscopic image. Here I have a macroscopic data set, and you can see area 1 has one surface texture, area 2 has a different surface texture, area 3 has another representation of the surface texture, and then I have the whole surface marked out. What is the right answer and what is the wrong answer? Of course, all the answers are correct for those specific areas of the surface. Just imagine trying to measure that with a microscopic. It's even harder to get stability of the surface. And of course, ISO do give us some guidelines. And within those guidelines, you can see the ISO, of course, You can always deviate from these guidelines if you so wish, but you should say so in advance. If we take the minimum RA, it gives us a guideline at 2 microns and a maximum at 10 microns. That profile length should be 12.5 millimeters in size. Of course, to do that and achieve that with any type of microscope system, you have to image stitch, and this takes time, and it can take much time. Whereas a macroscope system will clearly measure the whole surface within one single measurement, and measurements are very fast, concise, and repeatable. Here I have a measurement of a roughness artifact, and this is interesting because it really shows the spatial frequencies and the relationship of spatial frequencies to high frequencies. So as we go to the right, we've got lower spatial frequencies. As we go to the left, we've got higher spatial frequencies. And I've tried to demonstrate here where the macroscope is okay to measure. So the green ticks represent surface textures, which are rougher. We need sort of larger sampling areas to get stability of data as recommended by ISO. And of course, down at the higher spatial frequencies, you get to the crossover point. So when you're at 0.8, you can get a representation of texture, but you're really crossing over to microscope type systems then. And then you can see the crossover point. The image on the bottom, you can see the profile lengths. And interestingly, manufacturers produce these roughness artifacts. And if you're trying to measure them to ISO and you're doing it with a profile type instrument, you can see that it will be virtually impossible to zigzag your stylus across these surface types. So sometimes you need a tactical approach to getting data and to getting stability of data. For form measurements, here I have an additive manufactured surface, an artifact which has large triangular shapes on the surface. If you look at the scaling, the Z range is well over 1 millimeter. The practicality of measuring this with a microscope is not really ideal. Of course, the microscope will give you really good information close up, but if you want an overall view of the surface, then the macroscope could certainly do something in a much more practical way, which you would not want to take up as a challenge. In fact, when I first started measuring a sample, I had a go of it on the microscope, and I just said to myself, I'm just wasting my time. I'm not going to get any clear sort of visual representation of the surface in terms of how I'd like to see the overall landscape of this surface. And of course, the researcher who I got this from, he fully agreed with me. He says, you just wouldn't measure this with a microscope. And he's an expert in his field as well. So I've got some information here about calibrated artifacts. This first is a RA 1 micron from a Rubert standard. The first measurement here is measured with a ProSurf, the S system, so a smaller field of view system. And of course, you can see that RA equals 1 micron. You get a result. I then measured this same artifact with the microview. Now you can see much greater detail on this sinusoid. We can see the finer texture details. That's not noise you're looking at. That is the actual texturing of the surface. And you can see the sinusoid. And again, you can see that you're getting RA and SA in the order of 1 micron. What's interesting about samples like this is you can put a filter on the surface. And here I put on a 0.1 micron filter on. Sorry, I think that's millimeter. I've got the wrong value there. And you can see that you remove some of the high frequency information. So you're effectively applying an S filter. And you see that you actually have the same value because of the nature of the sinusoid. but you can see the whole story with this surface. You always have to ask yourself, how big, how small? Do I need to see these high frequencies, or are the results good enough for the application that I need? So moving on to my final case study. This is a real life case study for an optics manufacturer. And this is a case study about how to optimize the polishing process within a manufacturing environment. So you can see what we have here is we have some ground optics mounted on a polishing block, and they're attached through bitumen. So what happens is you have a mounting block, you have a fixture, you have your optics, you then heat up the block, you place the optics on through a masking tool, they're then pressed down, and then you take these pre-ground surfaces and you polish them flat. So here we use the ProSurf for measuring this. The polishing block here is 150 millimeters in diameter. The thickness of the optics is about 5 millimeters. You can see how we measured the whole surface with the ProSurf, and that measurement took less than 3 minutes. You can separate the bottom surface data set from the top surface data set, and you can see then individually each of the ground optics. So for this application, they wanted to optimize the polishing process. So what we wanted to do was reflect the relationship of the measurement to the polishing process. So ideally what we wanted to do was understand how the surface directly interacted to how it's being polished. So the first thing we had to do was understand how to level the object. If you go back here to this slide, you can see that we have a best fit plane through the data. Whereas what we needed to do was establish the contact plane. So we devised a special algorithm to analyze the whole data set and then to give us a triangulation to represent how this surface would then sit on the polishing plate. Once we've done this, of course, we could check the integrity of this contact plane. And here you can see how the contact plane would sit on the surface. And from there, we can now identify problem optics. So what we're looking to do is identify the optics which are not going to make contact to the polishing plane because they're not mounted correctly, or they're sitting too high, which could influence the behavior of how the other optics around it are equally polished. So here on the top, you can see an optic in blue. That's not in contact in relationship to the contact plane. And then on the bottom image, you can see a more rainbow colored optic. You can see this is tilted. And it's really easy to visually identify these optics once we applied the contact plane to the surfaces. So we have a really interesting function within our software, something which we refer to as pattern matching. So it's like a teach and learn. You teach the instrument what shape of the optic looks like. Then you can apply your mask and your analysis, and it doesn't matter the orientation of the component, it automatically does this. So it'll automatically statistically sort your components digitally, and then you can get digital processing on this data for export, and these numbers then directly relate back. So you can see here I've highlighted optic part number 10, and you can see that the maximum minimum distances from the contact plane are much higher than the other optics, and you can clearly see that this is a problem optic. This can then be remounted, and you can then optimize the manufacturing process for this particular setup. And this was something that was actively done within our instrument. Now, typically in this market, people would use a phase shifting piezo type interferometer for measurements, but because of the nature of how the surfaces are interrelating, they needed the coherent scanning over a large area. So this was a unique capability for the Polytech ProSurf product. You can then take that step further. Here you have a simple optic. You can see a pen mark there. We're actually measured the pen mark on the optic. It has a defect, and by applying the contact plane, you can apply it to any surface situation type. You can now see the total depth of this defect from its complete surround. So if you just did a small area measurement, you might think it's only a micron or two you need to remove. But when you compare it to the globalization of the surface, you can now see that you actually need to remove 3.6 microns of material to fully remove this particular defect. So conclusions, hopefully I'm not interrupting dinner too much or lunch. So the microview brings a new level of performance with its continuous scanning technology for micro step heights and roughness measurements. The ProSurf is one of our best-selling instruments into the macro market. It's particularly interesting if you're looking at large fields of view, flatness measurements, large steps or form. Both instrument types conform to traceable international standards, and we have full single press button automation available and supported with pattern matching. I thank you very much for listening. Thank you. I'm now ready for questions, Sarath.
Thank you so very much, Joe. This was really insightful, exciting, and amazing presentation, and laser sharp in terms of timing. Just exact what we were looking for. So
I'm so lucky with timing. That means I'm not delayed people's lunches. So thank you very much for that.
We are indeed grateful for that. So let's start some questions. So I can see one question coming. Do you want to start asking questions? Yes, then available to question. So one question is in the chat box from Shen Lu, Joe, which says, interesting to see the inconsistency of AM surfaces. Question is how big measurement areas I should choose to result a good local roughness measurement rather than large global measurement? Or if I have a large area measurement, how can I characterize local roughness variation?
Oh, that's such a hard question. I think the big trouble with AM, you have such a randomized surface. You have such inconsistencies. It's really hard to get that. And you might find that with a microscope, you'll measure one day in one area and it's okay. But then suddenly something goes very wrong with the process. And if you're looking at a small area, you may just simply not see it. We had a customer in Turkey who was looking at microscopes, and they almost went and bought a microscope, but they decided what they wanted was a roughness tester. And they decided that the high resolution of microscopes is fantastic and you get tremendous detail, but what they really wanted was the consistency of the surface. And so they went for a macroscope because the texture results were presented to them in a much more stable way, and it was much more statistically easier for them to relate the measurements to the process and then to control the overall process. So it almost removed the instability of looking too close to the surface. So I can't give you a yes/no answer to that, but certainly it's an advantage if you see more of the surface.
Thanks, Joe. Any other questions? I have two questions, Joe. My first question is, when we speak of roughness parameter, we all know we have RA, RQ, RT, and so on, SASQ, etc. And these are kind of good indicators to kind of scalarly or kind of develop a scalar number to know what the surface is like. In your experience, when we talk of functional correlations of a surface with, let's say, a particular functionality, whether it comes in terms of tribology or in terms of bacterial adhesion or in terms of other attributes of optical reflectance. Have you come across that a particular parameter has a stronger correlation with a particular functionality rather than all the other parameters?
Oh, absolutely. Every time I blink, someone from the ISO committee develops another parameter associated with a particular functionality. You have specialized parameters. Of course, the most common parameter, and the one I gave examples here, are associated with RA and SA. It's the most well understood parameter, but equally it's the most least understood and the most well abused parameter, because you can have very similar surfaces that have very similar results. And of course, you have to think back that parameters like RA were originally designed to tell you when you departed from a nominal manufacturing process. But if you then want to see maybe other information, maybe you're working with an optical surface and you want to see non-typical marks, scratches and defects, you start to use, for example, a parameter such as RQ. Then you may want to have a surface which is a bit more designer. Maybe you need to look at how a surface is sticking up or sticking down, and you use skewness. Then there are so many different parameters that will relate to different functions within the surface. Most parameters start off as amplitude parameters, then you get your spatial parameters, you get your hybrid parameters, you get your bearing ratio parameters, your volume parameters, you got your band pass filters, your high pass, low pass. They'll all tell you something different about the surface. And of course, you have to do your experimental setups to really understand and appreciate what parameter is most appropriate to describe your surface and its functionality.
Thank you, Joe. It'll be very interesting to learn more of that. One other question that I have, as you know, UK is currently thriving on digital technologies, digital economy, and everything going digital.
Mm-hmm.
And there's a great surge of push to use data analytics and AI. Mm-hmm. Where do you see the use of AI in your metrology operations?
Well, I can give you an example. We have one client of ours who has multiple systems for us, and they're controlling the texture of cold rolling processes within the metals industry. I won't mention names, but they simply have samples cut out periodically from the cold rolling strips going by. They then barcode them, so basically give them a serial number. They then measure them, and the operators, all their job function to do is collect these samples, barcode read them, scan them, measure them, and the data goes off to the big processing data bank in the sky. And the processes are so well developed that they can tell and see whether a surface is slightly tilted. They can tell whether the process is changing down to the micro nano level really quickly, and they can then product select those materials for the right applications. So we certainly see it happening. Companies will never tell you exactly what they're doing and what parameters they use, because that's their IP clearly. But you can see that the methods are already developed there, where you're trying to remove the operator, you're trying to add in automation, and you're adding in an element of artificial intelligence for these data processing. So it's certainly clearly happening.
Okay, thanks, Joe. Anybody other question?
Yes, can I ask a question, please?
Yes, Peter, please go ahead.
It's regarding your objective lenses. I'd like to ask you, are you manufacturing your own objective lenses, or are you buying these in from somewhere else? And what quality are they? Because the quality varies a lot, tremendously. So for example, it used to be the case that the people like Reichhardt were sort of the top line lens manufacturers, in contrast to some of the Japanese companies. I'm not trying to say nasty things about the Japanese lenses, but they were regarded as being slightly lower quality because they were less pure glasses and all this kind of thing. Do you have any comment on that?
Oh, absolutely do. You see the noise performance between lenses will vary, not just between different manufacturers and suppliers of lenses, but between different magnification lenses. So you'll find that the way the light comes through the lens, you'll see a different noise performance. But of course, you can suppress that. So first of all, Peter, thank you for your question. Secondly, we are just buying our lenses in, and we are using standard lenses as manufactured by another company. But then what do we do to control and contain any errors associated with those lenses? And of course, we have to calibrate them, we have to characterize them, we have to suppress the errors within our instrument and its configuration. So we fully characterize our Z translations of our instruments with an external displacement interferometer. We have to characterize the behavior of each lenses in terms of X, Y, and Z, so characterizing the optical wavefronts. We have to maybe allow for various methods of oversampling, smart scanning, averaging to improve the quality of the data set. So the quality of the measurement is not just down to the lens, it's down to how we signal process it using our correlogram technology, but then also all the other things to try and enhance and improve the individual performance of a lens. So the lens quality is part of the story, but then it's also how we look after the data and contain the data, which ultimately leads to the quality of the end result that we're presenting.
Yeah. Do you ever have any issues with astigmatism at all that you would have in normal optical systems?
Well, if you look at the lens and you look at the full form fill that you get with a lens, you will see that if you go for the largest demagnification you can get, then you'll see an inconsistency of the light throughout the total lens. So you will actually get a higher bright spot in the middle of the lens. And within our optical design, we've optimized it so that we don't utilize the whole field of view or the form fill of the top of the lens. Mm-hmm. We've optimized it so that we reduce those impacts. And by doing that, we optimize the consistency of the light presented to the form fill at the top of the lens. And by doing that, we then optimize and reduce. It's not necessarily the measurement associated with a single lens. These then impact if you start to do things like stitching. And the quality of the image stitching is really excellent at that point. And then we have two methods of stitching to enhance stitching performance as well.
So am I right in thinking that when you're using say a 100 times objective lens, which is right on the limit of light resolution, you need to, you're basically signing up to doing a lot of stitching. If you want to look at a very large area at relatively high resolution, you probably would need to use the 100 objective, but I can imagine there must be a time penalty. You can't just do
absolutely
hundreds of thousands of images.
That's why I talk about the ProServe. The ProServe, it doesn't have the high XY sampling rate, but if you want to measure a large area, it's just a different technology. in terms of its X, Y, Z. And I think you have to consider the practicality. With the 100x lens, for example, you have different slope handling, numerical aperture capabilities. We've gone for one that has a practical working distance and standoff. Some, I think ours is 2mm standoff. I've seen other makes of 100x lenses where you might have a little bit higher numerical aperture, but then you're down at 500 microns working distance. And that's not necessarily a very practical measurement methodology at that point, because you're at high risk of bringing your lens into contact with a sample if you're not careful. There's always a trade-off, and we like at Polytech to think we've balanced out the trade-offs for an optimized and practical measurement approach.
Okay, thank you.
Difficult questions, Peter, and there's no right or wrong answers on those, as I know, because that's why you're asking.
I'm just wondering.
Good questions.
So, Joe, one thing I thought to let everybody know for a wider benefit, although we haven't explicitly covered here except for metrology, but Polytech is probably a world leader in laser vibrometry.
Absolutely.
Want to say one or two lines about it?
Of course, for Polytech, of course, we are considered the gold standard for non-contact laser Doppler vibration measurements. These instruments are pretty much 80% of our optical measurement systems business. They're outstanding. I mean, you have picometers of sensitivity, and you can measure tens of meters in terms of velocity. And those systems come in single point scanning, and they come in rotational and 3D scanning configurations. And of course, the nice thing with a laser vibrometer is you can point it through microscope lenses, you can point it through long working distance lenses, and because it's lightweight, you can measure everything from a bee. You can't stick an accelerometer on a bee, notice and fall over, to lightweight materials, to dangerous hot objects. I've supplied laser vibrometers on people measuring electrical bars, and it's always nice to say to them, it's a good day if you don't die. And laser vibrometers, they're non-contact. You're not going to come into risk of anything, not touching something. A good day is not dying. Laser vibrometers are truly non-contact.
Maybe you want to say or mention, Joe, very quickly, what are the properties that you can measure through a vibrometer that people would know?
You can measure velocity, you can get acceleration information, you can get displacement information. So surface topography measurements are a static measurement technology. Normally, you're measuring a surface that's not moving, whereas the non-contact laser vibrometers is a dynamic measurement. So you're measuring how something is dynamically behaving, such as a speaker, an accelerometer, how a car is vibrating or sounding. You think if you buy a Porsche, you want it to sound like a Porsche. These vehicles are not just accidentally sounding like a Porsche, they're designed to sound like a Porsche. I once sat in on a Bentley presentation, and I actually pump up the exhaust sound into the cabin. So when the executive is putting his foot down, these things could run quiet, but they want the sound of grunt. This is what makes people smile. It's the smile factor. And of course, if you're talking about racing performance, noise and vibration is reducing your efficiency. So equally, you can fine tune your efficiency and do your non-destructive testing for optimization and enhancement of life and performance of any product.
Great. Thank you so much, Joe. If somebody has any question, then we are just closing in. Otherwise, just one last question. No. So you are relieved, Joe.
That's very good. Time for lunch. Thank you everyone for joining one more time.
Thanks,
and I
everyone.
hope you enjoyed my presentation. Any questions? I've been asked to refer and deflect questions through the DSM network. So it's adding to the community. And of course, I'm always available to help and share my knowledge. And once again, thank you for joining.
Thank you, everyone. I look forward to see you again. Thanks,
Bye,
everyone.
everyone.
Bye.
Bye-bye.